So this is called the Schrodinger. Quantum model. Invented by or derived by a gentleman named Erwin Schrodinger. Has a couple of dots over his name like that. And the Schrodinger model or quantum model is based upon the wave particle duality of the electron. In the evolution of the modern quantum model, it was discovered that the electron behaves in a particle fashion as well as in a wave fashion as it exists around the nucleus of the atom. Now, it was discovered that using what we call diffraction grating, a cathode ray tube had embedded in its center a diffraction grating. It had about 30,000 lines per inch, just on scratch parallel lines. And this was a cathode ray tube, meaning that it had the ability to fire a beam of electrons toward that diffraction grating. The short end of the symbology is a negative plus a transformer, something that generates a strong potential difference. So you have this beam of electrons being fired at this diffraction grating. Now, if the electron was exclusively a particle, then it should have passed straight through, unperturbed. But that's not what happened. What they found was the particles diffracted, much like the bright line spectra would diffract and form the bright lines. And these were diffraction patterns generated by the electron beam. Until this experiment was conducted, it was believed that only light, electromagnetic radiation, would undergo diffraction. Now they were looking at what they thought were particles like BBs flying through the air, particles of matter demonstrating wave behavior. Hence the terminology of wave-particle duality that we presented in the initial presentation. So, now, when it was discovered that the electron has a wave-particle duality, very bright scientists over history derived some equations that would describe the behavior of the electron or the character of the electron in terms of its wave and energy characteristics. And this was referred to as the Schrodinger equation. Now, the Schrodinger equation is a partial differential equation way beyond the scope of what we need for this course. If you stay in physical chemistry, you will probably be exposed to the Schrodinger equation in probably your junior year chemistry if you stay in it. But what the Schrodinger equation provides us is a method for deriving wave functions that are solutions to this equation. And these wave functions define character of the electron in terms of its wave energy content. One scientist came up with an equation, and I can't spell it, called the de Broglie. It's a very, very simple equation. It says for any material object, the wavelength of that object in motion is given by h over mv, where of course h is Planck's constant. M is the mass, the rest mass, I might say. Let me put that in there. And v is the velocity or speed, typically in meters per second. Now, for large objects like people walking around, the wavelengths are so long and the energy of those wavelengths is so low that we can't really detect them. You could put the weight of a 150-pound person in here and moving at 2 miles an hour walking or running and divide it into, and you'll come up with a wavelength, which is miles long. Okay, so it's really, it's applicable to macro level determinations, but where this comes into existence, it finds its value, is in the determining wavelengths of subatomic particles moving 80 to 90% of speed of light. And these are defined, once you get the wavelengths under their energy and their speed, from the speed and the wavelength, you can define the energy of the particles. And from that, you can describe the behavior of the electron in terms of its wave character. Now, what I'm giving you here is the first instance of saying that, well, particles have waves or function as waves. What this ultimately led to is the application of statistical mechanics to the wave-particle duality of the electron. Statistical mechanics is a study in probability and statistics. And this statistical mechanics, and when you apply probability mechanics, leads to wave mechanics. Now, I know it's stringing out, but there's a point to be made. When statistical mechanics is applied by probability in the form of wave mechanics, this leads to a entire field of study associated with atomic models called quantum mechanics. Of course, this is based upon the solutions to the Schrodinger equations and a lot of complexities that are way beyond the scope of this course in terms of the math and what we're trying to do here. But what it came up with, the first thing is it allowed us to define the behavior of the electron in terms of what we call quantum numbers. To define an electron in terms of quantum numbers requires the use of what we call 4 quantum numbers. So what I'm giving you here in this statement is very important in your perspective on what I'm trying to teach you. When we talk about quantum number sets, that set applies to only one electron. There may be hundreds of electrons in the electron cloud surrounding the nucleus. But if we pick an electron, it's defined by a set of 4 quantum numbers. And this gives what is called is based upon what we call the Pauli exclusion principle. No 2 electrons have the same set of 4 quantum numbers. You know, you're using Qn to define quantum numbers. Now, the significance of this is when you consider the large elements with 92 electrons buzzing around them at close to light speed. They don't run into one another at all. So why? It's because each electron has its own set of quantum numbers. And this set of quantum numbers is referred to in the community as an energy window for each electron, that no other electron can occupy that energy window. So we're going to learn how to assign those numbers for test taking purposes in this. Hopefully, if I got time, I may have to carry it over. But once you see how to do this, it's very simple, it's very straightforward once you follow me along. Now, everything I've given you is just kind of a historical evolution of the idea of using quantum mechanics. Now, we're not doing the math of quantum mechanics. That's, again, way beyond the scope of the course. But we are going to look at the conclusions and solutions to quantum mechanics which apply to these quantum numbers. Okay, so the four quantum numbers include principal, and that's given by n, orbital, given by a lowercase l, magnetic, lowercase m, and spin, m sub s. Those are the four quantum numbers. And you can remember these easy enough, POMS, like pom-poms. The principal quantum number defines the location of the electron. In terms of its principal energy level. Earlier in the Bohr model, I told you, well, each ring is n equal 1, n equal 2, n equal 3. Well, that's what the principal quantum number says. What ring is it in? We're talking about an individual electron. Orbital defines the shape of the sweeping out in three-dimensional space. I handed you a orbital diagram, and those are what the orbital quantum number show you. That's this thing. So everybody should have a copy of this. So the orbital quantum number defines shape of electron orbital. And you will find things like S, P, D, and F. And we will relate to S, P, D, and F numerical values. Magnetic refers to orientations of that orbital. In three dimensions. If you look at your handout, you'll see that there are three orientations possible for the p orbital. Only one for a sphere. For d orbitals, you'll see 5 orientations. 7 for the f orbitals. We'll develop that a little more in a minute. And the spin quantum number is self-explanatory, of course, the rotation. Now there's simply 2 rotations, clockwise and counterclockwise. The clockwise is always a plus 1/2, and the counterclockwise is always a negative 1/2. And we'll explain these as we go along in the assignment. So for a given electron, to describe its character and its nature, you need those 4, and they are presented in an N, L, M, and M sub S format. And each of these will be numerical values. And no other electron will have that set of 4. Now, it's real easy to determine. Just bear with me. Right now, it's probably very confusing. I'm trying to be as logical as I can. Now, at this point, I could spend the rest of my life trying to explain how to get those 4 numbers in a conventional way, much like the books do. But I found a much easier way for the student, and that's to jump over this and explain how to write electron configurations using the Aufbau principle and Aufbau diagram. Many of you have seen these in early courses that you may have sat in, and that's 1s2, 2s2, 2p6, and those kind of issues, in defining what we call the electron configurations of elements. Once I finish and teach you some of that, then it's easier to go back and assign the 4 quantum numbers from that. I'll show you. The notations that I'm going to use revolve around what we call the Aufbau principle. Which states electrons in the building up process of forming the electron cloud enter at the lowest available energy level. Some people refer to this as order of filling, putting electrons about the nucleus of the atom, depending on what element you're trying to define. Well, this order of filling is based upon the Aufbau diagram. The handout that I've given you here is an Aufbau diagram. One shows an increasing sequence, whereas another one shows a top-down sequence. I always use the top-down sequence for specific reasons and for academic reasons. So keep that in front of you so you see how it evolves. Now, the Aufbau diagram is based upon in itself quantum numbers. N, L, M, and M sub s. Primarily the first 2. So what the Aufbau diagram starts as is using the principal quantum number. And what it means is the location of the electron. What ring is it in? All right, now how many rows do we, now right here, you should understand this from what I've already said. How many rows does the periodic chart have? you see 7, right? So that's where we want to start. Now, theoretically, it can go to 1 million, but what we know of in reality is 7 rows on the periodic chart. Okay, so start under N, which is the rows. 1, 2, 3, 4, 5, 6, 7. Just straight down. Pretty straight, huh? Pretty easy. So that's your principal quantum number, N. Now you follow with the L quantum number, the shape quantum number. These refer to sublevels that exist within the principal quantum number. The principal quantum number, 1, 2, and 3, also define the number of sublevels that are possible within a given ring. For example, 1 would only have 1 sublevel. 2 would have 2 sublevels. 3 would have 3 sublevels. And 4 has 4 sublevels. 5, 6, and 7. And if you go to 8, it'd have 8 sublevels. Now, the L quantum number is the shape. So L quantum number starts with an S orbital. So you always have to use up the S orbital first. You can look back at your diagram that I gave you. You need to get that in front of you. It's in your stack of papers. You need that in front of you. So we're starting with that sphere. And so everything under that S is going to have, this S, every orbital, principal orbital is going to have an S orbital in it. Now, the first ring around the nucleus only has can only have one sublevel, S. So it doesn't have a p orbital. But when you go to 2, it does have a p orbital. So it would have, this one is called a 1s, and then you get the second ring, you have 2s and 2p. So that means it's in the second energy level, and it has a p orbitals, or a set of p orbitals. And you get down to here to 3, you can include the d orbital, and you get down to 4, you can have an f orbital. If you get over here to 5, you can theoretically, you can have a g, an h, and an I orbitals, but these haven't been invented yet. And that's what the quantum math shows us. Third energy level, we can use up to d orbital, but not f, I, g, h, and on. So that'd be 3. In the third energy level, we have a 3s, a 3p, and a 3d system. Now we get down here to the fourth, we have room for the f orbital now. So that's 4s, 4p, 4d exist, and we'll have a 4f system. That'll be the first row in the lanthanide series at the very bottom of the periodic chart. In the fifth row, we have a 5s, a 5p, a 5d, a 5f. Yeah, you can have a 5g, but it hadn't been invented, so I'm going to put a parenthesis around that just to indicate it's kind of virtual in the diagram. It's like extra digits in your calculator answer. It's there, but we don't use it. And 6 does the same thing. It has a 6s, 6p, 6d, but you only have 2 rows. Look at the bottom of the periodic table. You only have 2 F series. So you can have a 6F, but it hadn't been invented yet. 6F, G, and H. But these have not been invented yet. And down here the 7, excuse me. 7S, 7P, I think, are the only ones that have been developed in that context. You only have 4d orbitals. You look. See, when you look at the periodic table, you can tell how many you have. 1, 2, 3, 4, because the transitions will be building the d orbital. So anything after 7p is also virtual. They're all P, D, 7F, 7G, 7H, 7I. So, you know, the outbound diagram evolves because of the quantum numbers as we go through this. Now, how do we use this? The use of it, as you see in the diagram that I've given you, is the order of filling. These red arrows show how many you put in. So first you want to fill the 1s orbital, then go back up to halfway between the two arrows, go back, and then you fill the 2s orbital, then go back between the arrows and fill the 2p and 3s orbitals, and you just keep meandering your way through the outbound diagram, and it shows you the order that we fill. So we're going to have the 1s filled first, and then we'll go back up, and then we'll fill the 2s and go back up, and then we'll fill this one, and we'll keep doing that. And this is the order of filling. And of course those don't exist, so I'm not going to scratch those out. So what does this lead to? Okay, the largest element that we know of, starting with the 1s, and then we go to fill 2s, and then we fill the 2p, and then the 3s, 3s, then the 3p, right here. Go to 4s. Now notice how it comes back up to the 3d. I'll show you where that's significant here in a little bit. And then you jump back into the 4p, fill 5s, and then back up between the arrows, and it's 4d, 5p, 6s, and then back up. I will show you a shortcut later. 4f, 5d, 6p, come down here, and 7s, and back up to 5f, 6d, and 7p, and that's where it kind of fills up. Now, how many electrons can you put in each suborbital structure? Well, that's one thing you got to learn. S, P, D, and F. And it's pretty easy. Now, this can hold a maximum of 2, 6, 10, and 14. Now, there's a logic behind it. When I talk about orientations, I'll show you that, where those numbers came from. So those are the max number of electrons you can put into each suborbital structure. So I'm going to use red to put the electrons in. The electron symbology is you use superscripts, and the s orbital can hold 2. So I'm going to put a superscript 2. That means 2 electrons are filling up that s orbital. Now we go to 2s. Well, it can only hold 2. But the p orbital can hold 6. The s orbital back to 2, and then p is 6, and we keep doing this. Notice d has 10, so I'll fill it at 10. 6, s is 2, d is 10, p is 6, s is 2, f is 14, so we got 14 in that one. D is 10, p is 6, s is 2, 14 for f, 10, and 6 max. That fills up, that's the last element on the periodic chart down there. Now, that's all well and good, okay, to be able to meander through this and write the big long sequence of symbologies. But that's not what this is ultimately for. What you want to do is write what we call the electron configuration of a given element using this pattern. Now all you have to do is be able to read the periodic chart and define the number of electrons in the element for writing out the what we call the electron configuration for that element. Right now we're going to work with neutral elements. That is, the number of electrons equal the number of protons, which is the atomic number of the element. So if you pick hydrogen, we'll start off with number 1. How many electrons does it have? 1, because it got 1 proton. So in looking at this big list of stuff that I've got up here from the Aufbau diagram, all we need to do is put in 1 electron, and that's got to go in this first level. What does the Aufbau principle say? The entry of the electrons have to go into the lowest available energy level. Well, that's the 1s orbital. So what we symbolize that is we put hydrogen, put it in brackets like that. No, let's go somewhere else, sorry. Just put hydrogen in a colon like that. And its electron configuration starts with 1s, and you put 1 electron. So there's your electron configuration for hydrogen. Now let's jump to oxygen. Oxygen's number 8 on the periodic chart. So how many electrons do we need? 8. So I look up here at my big pattern over here. I got 2, 3, 4, 5, 6, 7, 8. So I need to stop right here, but only put 4 electrons on the p orbital. So for oxygen, I would write 1s2, 2s2, 2p4. Now that's one way to write. There's a couple of others I'll show you. We're running out of time, so I'm going to just give you the basics here. So you can go anywhere on the periodic chart now and simply pick out the element. Go to chlorine. Okay? Cl's number 17. This one's number 8, and that's 1. So I need 17 electrons. So what am I going to need? So I'm going to go out to the 3p orbital, and I'm going to put only 7 in that 3p orbital. And if you count it back, I look for the 3p, here it is, right here. Okay? Now I want 7 electrons in the outer shell, let's put it that way, in the 3rd energy level. So I'm going to have 1 less than 6. I'm going to have 5 right there because I'm going to have 2 already in the s orbital. So chlorine would be a 1s2, 2s2, 2p6. See, those first 2 rings are full. Then you go into the 3rd ring. The highest principal quantum number is your leading number, that's 3. So 3s2, that's filled. And then you have a 3p set of orbitals, but you only need 4 electrons in that p set. Because 4, 5, 6, 12, 13, 14, 15, 16, I'm missing 1. Oh, 5. I should have a 5 there, sorry. So I should have 17, 17. Add them up, add up the superscripts, you have 17 electrons. That's one way to do it. Now, when you get out here in the, say, you get up to calcium, look at number 20. Calcium is right here. You're up to 20 electrons. But what happens at scandium? Okay? This is a 4s orbital. So what happens after 4s? Who do you fill? It goes into the d, and that's when you enter your transitions. So all of the transitions in here are filling using the d orbitals. You'll find that you go along here, and then when you start filling up the lanthanides and actinides, you're filling f orbitals. So you have to take that into, and it'll show you we had steps down. See right here? Now, when you get here, one of the things you'll get used to, if you work with this, is when you get to, say, finish calcium, and let's say you need scandium. Well, this would be a 1, 2, 3, 4 S2 for calcium right there, but it would be a 3 D1. That's where one right there. Now, Ds can hold up to 10. So if you count the blocks, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You go, so D1, D2, D3, D4, D5, D6, D7, 8, 9, and 10. So that one has a D3, D10 now. And then what happens after the 3D? You go back into the p orbital. All of those over here on the right of the periodic chart are filling by p orbitals. Over here, that's what it's showing. P orbital filling. And then once you get it full, you go to through, let's see, right here, krypton. Then you have to start over with 5s and go from there. These first two columns are always s orbitals filling. The groups over here, the main group 6 over here, are p orbital filling over here. Then those in the block center are all d orbitals, and those at the bottom are f orbitals filling. And every time you reach one, you step back a principal quantum number. This one says 4s2, but you got to drop this one to 3d. When you get here, this will be a 5s, and then you'll drop to 4d. See, in the iridium. Here is cesium, barium. Those are in the 6s, but you'll drop back to, for lanthanum, 5d, for d1. So every time you step into the transitions, you drop back. And you can confirm this up here. But I'll show you in the next class how you can just go anywhere in here and write out the configuration. Now there's one little short thing I want to show you before we close today. And I hadn't gotten to orientations yet. And that's where we will start the next time. Now notice chlorine is right here. And then argon follows. Well, whatever I write for chlorine, everything in here, and I go to krypton, well, argon, yeah, number 17, I have to rewrite everything up here. But I put one more electron in. See how I did that? Well, there is a shorthand method that's accepted in the scientific community. All of this, short of the last outer shell, this is called, the highest principal quantum number here is, of course, your valence shell. That's your valence. So what I'm going to do, see, these refer to the previous row's noble gas configuration. So when I get to, I'm going to do chlorine and then argon. So I can write chlorine in this format. That's where I use the brackets. I go look in the previous row from chlorine. So you come up here to chlorine. Where did you go here? Previous row's neon. So everything's going to be neon until I get into that third row. So I'm just going to put neon in here. And then start with the 3s2, 3p5. There's chlorine. So all I need is 5, 6, 7 electrons. Fill up at 8. And then the same thing with the argon, number 18. I look at the previous rows, and it's neon also. 3s2, 3p6, and so that one's full. So instead of writing all of the stuff from the previous row's noble gas all the way back to hydrogen, just put in brackets, and this is the configuration up to that point. So if I looked at iodine, for example, I want the configuration for, let's do 10. I want the configuration for 10, SN. So it's atomic number 50. Well, I'm not going to write out all the configurations. What I'll look is krypton and just concentrate on the row that it's in. Now, it will contain a drop down for the D. So when you go to 10, you'll start 1, 2, 3, 4, 5. So that's 5s2 is where I'll start. See, I've already got the krypton, so I'm going to start only in that row. No, excuse me. I'm going to start in rubidium, so that'd be 6s2. Sorry, 6s2. So we start with the rubidium, then strontium, then we drop. See, 6 then goes to d orbital, and it drops down to D, so that's 5d10, because we went all of through the d orbitals right here. Rubidium and strontium were s orbitals. Then the transitions are all d's, but they step down one number, and then you come over here to indium and 10. Well, it jumps back up to p orbitals here, and that goes back to 6p, and you have 2 blocks. One for the indium, one for the 10. Yes, sir.
Did we skip the F orbital for 4?
Does it have an F orbital? No, it doesn't have it in that row. F orbital's not in that row.
But it should be in.
Huh?
It goes from 6s2 to 4f14.
The F orbital's not in this filling row. Run it across, and you'll see if I've got it in that. You don't have a 4F in that one. It would go through 3D, 4P, 5S. Then you got 4D fills up. You got the 5P, 6S. Okay, I'm in the wrong row then. I'm in the wrong row here. 1, 2, 3, 4, 5. Because see, iodine is in the 5th row. So this has to be 5s2. So I was right the first time. So that's a 5s2. Because see, here your I got another periodic table somewhere. Well, anyway. See, you have to get down here before you get into the rare earths. So if this is in the 5th row, this is a 5s to here. And this is a 4d until you get to here. And then you get 2 more, you have to go back up to 5p2. That's what, okay? I just misfired on the row I was in. Okay, guys, I'll pick up here in the next class.